Yeah, hello friends, welcome back. So in the last video we try to write the drivers for the GPIO, and this will be the part 2 where we'll try to get the UART working, mini UART working. Okay, so in the last video I think I have explained till this make file. So make file I didn't explain in the last video, I just copied it, and I think if it needs explanation, please comment in this video, I will explain this. But my focus will be on explaining the C code and assembly code. Okay, so that's why I will directly jump to that. So in this video I will try to write the main function, and before writing main function we need to write the UART drivers also. So UART drivers, for that I have to create a separate file. I will create, that is one header file also I will create, and then one C file. That header file I will create inside the include directory. Let's name it as mini uart.h, and let's create a uart.c file inside this one. Mini uart.c, sorry, mini uart.c. Okay, so I think before starting on the mini UART, let me first let's go through the data sheet of the mini UART. Okay, so data sheet of mini UART I will open. Okay, so this is the data sheet for BCM2837. Inside this, this is the mini UART section. First we'll understand this mini UART section, and then we'll start on the function implementation, driver implementation. Okay, so this is that section, auxiliary section. So here actually we have total 3 peripherals, UART1 and 2 SPI modules. Okay, inside this they have given this is the basically register map for that auxiliary peripherals. Total 2 UARTs are there, UART0, UART1. We are going to use the UART1 okay, for getting the UART prints. Okay, so here for enabling each of this peripherals, they have given one interrupt status. This one is for interrupt status. This they have given auxiliary enables. So I think bit 0 is for UART1, and bit 1 and bit 2 is for SPI1, SPI2. Okay, so this is for that one. Then this is for reading and writing data to the TX and RX FIFO, this IO reg. And then if you want to do interrupt based UART, we can use that also. But in this implementation I will not go through interrupt. I will not do interrupt based implementation. We will poll it basically. Okay, keep polling one register, and then based on that, that register will be basically to receive. There is a LSR register, and that LSR register is here LCR, MCR. I will tell about when I will go through this register sheet. I will tell which register we have to keep reading to find out whether the symbols are there in RX FIFO or not. Okay, so if I have paint here, I can explain basically what is RX FIFO and TX FIFO. So basically you consider it as a 2 FIFO, where whatever character you want to send, you have to put inside TX FIFO, and before reading there is a status bit that you have to check. If that status bit shows as a 1, then basically you have one character in the RX FIFO, that then you have to read from there. Okay, that's it. So for configuring this mini UART, we need to do this enable. Using this IO res, we have to do read write. We are not using this interrupt enable, so we'll write this as a 0. Then we have line control, modem control, and one UART extra control and baud rate selection. Okay, so basically these are the registers which we are going to use to configure the mini UART. Okay, so here you can find bit 0 is for mini UART, and auxiliary enable. Okay, same, this one is for IRQ status, and this one is for auxiliary enable. So this IRQ status we'll be using if we want to go through interrupt based UART. Okay, if you implement interrupt based UART, then we will use this IRQ, otherwise not needed. Okay, so that one will not use. So this one is for enabling. And inside mini UART we have 2 modes of operation. One is 7-bit and 8-bit operation. So we are going to use 8-bit operation. That actually this is the way how to find the baud rate, how to set the baud rate. Our system clock frequency is 250 megahertz. Okay, so based on that only we will program the baud rate. Okay, so that is one thing. I will only highlight the important things which are there in this data sheet. Okay, so next is this one is not, we are not going to modify this. Then IAR register, no, this one also we are not going to change. Yeah, so this register we are going to set to make UART work in a 8-bit mode. Basically you have to set it as a 1 to this 2 bits in this register, LCR register. Okay, after that this modem control we don't want to use, so we will set it all as a 0. Okay, so here they have also written key write 0, so that's why we write this MCR register as also as 0. then this is LSR register. Okay, so this register is what we have to basically read to find out whether we have to basically read if there is any data in the RxV4, or if the TXV4 is empty, then we have to write inside the TXV4. So basically this bit 5 will tell yes, the TXV4 can accept at least 1 byte, then we have to write inside TXV4 to send data on the UART. And if here this bit will be 1, then basically we can read from the RxV4. Basically 1 character is available to read from that RxV4. Okay, so this register will be helpful, that LSR register. Okay, after that I think we have to set the baud rate register. Okay, no, apart from baud rate, before that baud rate we have to set this control register also, where we will be using for enabling the transmitter and receiver FIFO. Okay, so if you have to disable it, you have to write it as a 0, and if you have to enable it, we have to write it as 1. Okay, so this one also we are going to use, and this one stats we are not going to read, the FIFO stats. And yes, so baud rate, this one is also the important register which we have to write for the baud rate, for setting the baud rate. Okay, that's it. Okay, that's it, that will come. So if we program these 2 registers, then we will be able to configure the UART. Okay, so now let's go to the code where we are writing the, let's go to the editor where we are writing the code. Okay, it's getting locked every time, no problem. Okay, so now we'll start. So basically before doing that, let me show you one more thing. I think I have discussed previously also, RPI 3B GPIO headers. So which UART we are going to, which pin we are going to use, we'll go to that RPI model. So here can you see this or not? So here, is this visible? So here if you see, right, we are going to use this GPIO 14 and GPIO 15. So as I have told previously also, I am using one USB to TTL logic converter. Inside that we have total 4 pins. One is TXD, RXD, power and ground. Okay, you have basically 2 power source. One, either you can connect 3.3 volt or 5 volt, any of them is fine. So connect power to power source, ground to ground, and the RX of that TTL logic converter you have to connect with the TXD, and the TX of the TTL logic converter you have to connect with the RXD. Okay, so this physical connections are fine. So physical connections are also okay. Now let's so those pins we are going to use. So basically let's write a function to basically initialize that UART module inside that UART init. Inside that, basically what we have to do, we have to first set up that GPIO pin number 14 and pin number 15. And okay, so one more thing which I would have told in the previous video, in the GPIO video, that those GPIOs can work as any of the alternate functions. So total each GPIO can perform 6 functions, so we have to select which function it has to perform. So let me open that data sheet again, and there I will show you. So if I go to GPIO section and just go to this section. Okay, here you can see, right, here we are going to use GPIO 14 and 15, and we are going to use the UART 1. So we want alternative 5, we want these pins to be for pin number 14 and 15 to work as an alternate 5 functionality. Okay, so that's why to set it as alternate 5, we have to set one value. That value is also given inside this data sheet. Let me just show you. I think that value I have told you in the PPT which I have uploaded in my channel only, where I have discussed the GPIO. Okay, so I have to select the alternative function find, so I have to set it as a 010. Okay, so let's start writing that function. Let's start writing that function. Okay, so here, right, we have to initialize mini UART. Let me first call that GPIO function, GPIO pin set function, that pin 2. Yeah, so this one we have to write that 10, right, and pin 15 also you have to write is at 10, then GPIO pin enable 15 and 14. Yeah, so this will basically set the function of those 2 GPIO pins and then enable those GPIO pins. Okay, now we have to write this auxiliary we have to write some of the control registers of the UART Okay, so to write that, basically we have to create a header file similar to like this GPIO. Okay, so here I have already created that header file. This header file, we have to basically define whatever is defined in the dataset, the way which we whatever we did in the GPIO.h. Okay, so let me include hash let me include common.h, include hash include then common.h, and let's include pragma once, so that this file should be included only once. Okay, after that we have to include the base address also, but let's first define the structure as struct, and then auxiliary registers. Okay, let me check. So this one is 32 IRQ, and then enables, then reserved, then MUIO. Okay, so let me show you this also. So if you try to see here, right, let's go to the mini UART. What we are trying to do, we are trying to basically format this inside in one structure. So we have IRQ enables, then IO reg, IER, same thing I am doing exactly here. IRQ enable, then enables, and then reserved one. Here I am putting reserved one because if you see there is a gap from this 5004 to 5040, so total 14 32-bit space is there. Okay, so this is given in hex. If you convert in decimal and then divide it by 4, that many 14 you will get. Okay, that many bits are reserved, so that's why I have given reserved. And then mini UART, IO enable, then IER, then IAR, LCR. So all this register, whatever is given till here, till the mini UART baud rate, all that it came automatically. Okay, so this is what they call vibe coding, right? So that's why it came automatically. Okay, I don't need to do. Okay, so this is fine. I will minimize this. And next is that this is done. Then we have to basically how to basically read and write, right? So for that purpose we are defining this. It has defined reg aux, then structure pointer is fine. Okay, this peripherals base, this peripheral base also you can easily find in the this document, this peripherals base. If you go here, there should be, yeah, so this is 215. This one is the peripheral. From the, this is the 7 is the base address for the peripherals, and from that base address of peripheral, the offset for the auxiliaries peripherals is 215,000. Okay, so that's what I have added here. Okay, so this completes this thing. Problem is we need the definition of this p base, so that one we can include from this peripherals base.h. Okay, so basically this auxiliaries.h is completed. Now we'll go to mini UART.c. So inside mini UART.c, basically we have to write those registers to basically enable that to enable the mini UART. Okay, so let's start writing on this one. Okay, so this pins we have already set up the function of the pin and then also enabled it. So now let's start reg, then auxiliaries enables, we have to set it as a 1, correct? Then we have to set the mini UART control as a 0. Okay, during configuration we will set it to 0, then again we'll enable it to basically both the TX and RX transceiver and receiver both will enable at the last after doing all the configuration. Okay, after that we have to set the LCR register. LCR register is basically used to set the 8-bit mode. Okay, then MCR register we have to set that modem control signal, so this one we are not going to use, that's why we have disabled it. Then we are disabling the interrupt also because we are not using interrupt base. Okay, after this we have to set the baud rate. So baud rate we have to set it 270 because if you want a baud rate of 115200, we have to set it to 20, and this is assuming not 3 megahertz, this is 250 megahertz system clock, 250 megahertz system clock. Okay, after this basically we have to whenever I try to put shortcuts and all it. Okay, so next I will go to that next line here. Then we have to enable that MU control, again enable the transmitter and receiver. Okay, so after this basically this completes the UART init. Okay, after this UART init, basically we'll write a function to basically send any character and receive any character. Okay, so this one also it is giving, so basically AI is enabled, right? That's why it is automatically reading. So I will explain why it has written like this. So here we are trying to read the LSR, means I have told you right here there is a way to find out whether there is where the TX FIFO is ready to accept 1 byte or not. Okay, so that we read, and if that is not equal to, basically we are checking that particular bit should be 0, then while will become 1, then we are basically writing. Okay, so let me show you that register first. This is UART bit mode. So 5th bit, if this bit is read as a 0, then at least we can write to this one. Transmitter is empty, we can write to this one. That character will be sent to the on UART. Okay, that's what we are trying to do. So here we have to do, basically we are reading and we are comparing with 0, or either you can do the other way. We can remove this 0 and do not operation of it. Anyway, it is fine. Okay, and so whenever you are send, if this is that condition, until this condition is not met, it will not proceed, and if this condition is true, then it will directly write that character, whatever has been sent here, that it will write, okay, to the UART. Next, we have to write the receive function. Okay, receive function is also, it came here. So here what we have to do, basically we are trying to check whether data is ready inside the RxV4 or not. Only when it is ready, then we are reading and then returning that value from this character receive. Okay, so these two functions are basically done. Okay, we are trying to just mask with because total 8 bits character we are returning. Okay, so this completes our UART send and UART write. Now we'll write the main function. So basically we have to, inside main function, we have to basically initialize the UART, then print something on the UART and receive something from the UART. So those things we'll try. Okay, so let's start writing the main file. Okay, so here, as I would have shown you before, here we are jumping to which function? Kernel main function. Okay, so this kernel main function will define here. Okay, so void kernel main, and instead of looping in while loop, before looping in while loop, we'll first do UART init. Okay, after that UART init, we have to basically we will send some character one by one. Okay, it's showing as hello. Okay, and we have to receive also. Okay, hello world, it is automatically coming. It will do this, and then we can also receive. Okay, this is for sending, and we can receive that, but this whatever is sent from here, that will get on the UART, but whatever is received right now we cannot print it because we cannot print it. So this is sent on the UART that you will be able to see on the serial console. Okay, so we are not sending anything from the from that serial console which will be print here. Okay, so that one we'll try after this. Okay, so kernel.main is also completed, but before compiling, we have to include the UART, wherever UART send is defined. I think we have not defined this header file, so basically we have to define this inside header file. Okay, so let's directly copy now. This function we can copy from here and define in mini1.h. Okay, wait, sorry, where UART. Oh, what happened? Control C, then we have to paste it in mini1.h. Okay, so the UART receive also, UART send, UART receive, and UART init that. Okay, so this we have defined it here, and then where is main function? Then here we'll include peripherals aux, where it is in utils mini1.h. Okay, now we'll try to build. Okay, let's do make clean, and let's do make RPI. I'm building for RPI version 3. Okay, what it is saying? Okay, we have not defined the linker script. Okay, so let's define that linker script. I forgot to define the linker script, and before and after building this, actually I am copying to one location. That location also I have not defined here. Is there anything where I can send this? So there is a CD play with bits is there. Here already I am making this, so not inside this. I will keep outside this. Just create a directory with bare metal image. Okay, where I will put this image and then copy. Okay, so let me go to that directory and then just copy this location to boot mount. Basically, after building that image I am copying, there will be a lot of other temporary files which will be generated. So instead of going and searching there, I will be directly basically pasting here. Okay, that's it. Now we have to define the linker script, because here we are giving the linker file to basically build this kernel image. Okay, and that linker file we have not defined here. So linker.ld we have to define. That we have to define inside at this level. Okay, so what is the linker.ld? Okay, so let's write this linker.ld file, and inside this mostly we have to define some sections. So that sections let's define that sections. You have to define boot section, text section, arrow data and all. So that will define text section dot boot. So this section we have defined in the boot.s. So that will be the, after compiling, I want that code to be the starting point of this kernel image. Okay, that's why I'm defining this section first. Okay, so we have to write it text dot boot. Okay, so this one will put, after that I will put the text section here. Okay, so text will be put here dot text. Okay, after text I will put arrow data section. After that, arrow data will be kept inside the image. So all this, the way the way you are organizing here, the same way it will be organized in your binary. If you see the disassembly of that your binary, you can clearly see, okay, it is organized in this way. Okay, I will show you that disassembly also. Okay, so basically here also you have to basically do arrow data, and then data section you have to keep here dot data, and after this this way this should not be curly braces, it should be this bracket. Okay, let me change it. After changing this so till data we have done. Then basically that BSS section should be aligned to 8 byte boundary. That's why we have to do this align to 8 bit. Okay, and once it is aligned, then BSS will begin from there, and after that the .bss section will be kept here. This one should be star.bss. Okay, after this we have to basically do bss underscore end, and that's it. So this should be the content of that ld file. Okay, now let's try to do build. Okay, so what it is saying inside src. Okay, the location it is asking inside src. So okay, let me move it to src only. So this we have to can directly move from here to here. Yeah, so it is moved to that one. Let me try to build make clean. Okay, so it is telling there is no such file or directory inside gpio.c. I think I should mention that peripherals, because it's not directly inside inside at the same folder. It is inside peripherals gpio.h. Okay, any other error it is showing right now? Not. Let me build again. Okay, so this uint 8 is also not visible to which file? src.gpio. okay, inside this. So basically we have to include common here. That common is inside common we have defined this uint64 and all. Okay, apart from that any other error in base.h? It is showing some error. Where is base.h? Inside base.h. okay, we don't need this side. Okay, so this also is fine. And inside gpio.h what it is showing? Okay, so this one should be closed. Okay, any other error? No. So this is fine. gpio.c we have already included common.h. utils.h u64 is not visible. So where is utils.h? Why it is not visible? u64 we have defined in we have defined this u64 somewhere, right? utils.h, no, we have defined all this somewhere, common.h. So u64, okay, this u64, u32 and all we have not defined. I remember we have defined somewhere. Let me check. So u32 and all we have defined where? I'm checking that. That is defined in common.h, right? This is common.h. So we have defined it for reg. Okay. So for reg we just need 32. Even 32 we have defined. Okay. This volatile is okay. So here, let me change this to u64, then u32, u16, u8. Okay, so this is also fine. This should be also fine. Okay, let's do clean build again. Okay, so it is saying auxiliaries are not defined inside the mini UART.c. How come auxiliaries are okay? Headers are not included. Hash include mini UART.h is fine. Auxiliary we need, RPI we need. Utils, what is defined in utils.h? We are not using any of that, so no need. Again do okay. So now it is saying implicit declaration inside mini UART.c of GPIO. Okay, hash include we have to include the GPIO.h. Utils is not required, by the way. We need to include peripherals, then peripherals we don't need base, we need GPIO. GPIO I have already included, right? Then this function I have not declared in GPIO.h. Okay, let me check. GPIO.h doesn't have those functions which I have defined in GPIO.c. Okay, so instead of that, I think we need to make a different header for GPIO.h outside that peripherals, because this GPIO we have just used to define the structure. Here we'll again define one new GPIO.h. okay, GPIO.h. okay, inside that we have to basically define this function GPIO.h. we have to put it here, and then again next function GPIO enable also came. Okay, let me copy and put it there. Okay, so we have to include both of them in the mini UART.c. So in mini UART we have just imported this GPIO.h. We have to include just GPIO also. We don't want to include utils GPIO.h. okay, that's why this will not come. And inside no such file or directory which boot as. Okay, inside boot as what it is telling? sysreg we have defined inside peripherals. Somewhere we have defined, right? Inside include. Okay, so I have to define it from the source. We have to define it in include /sysreg. okay, sysreg. Okay, maybe name I have okay, name is wrong because I thought why this is needed. sysreg.h, make clean, and let's we got the solution. So inside this function I was not setting this semicolon, that's why. Now let's compile it again, and we are seeing some error inside boot as. Okay, let's go to the boot as, and here I think we are missing some line number 28. We are missing some comma on line number 28. Okay, this is done. And move stack pointer, this also we are move as p. Okay, so this is also fine. Now let's build it. Okay, we are facing at one more place, that is line number utils.s. we are facing at line number. Okay, so this comma should not be there. Let's build again. We are seeing some syntax error, and which line? Syntax error in kernel 8 img. Okay, linker script. We are seeing some issue in linker script. So here okay, this one is not required, I think. Okay, and inside linker script we have to tell this as this one is required here, and then this one semicolon is also required here. Okay, now let's build again. There is still some issue in this linker script. Okay, sections bss end bss semicolon, okay, and then align, then data, row data, then text dot boot. Okay, let's compile again. It is still showing some syntax error. Line number 4, what is that error? Dot txt. Okay, we need this space is what is needed. Okay, so that space is fixed now. Undefined reference to mem0. Okay, so inside utils function we have not defined mem0, so mem0 need to define. Okay, that will define inside utils function. Okay, that utils function will define. Okay, so let's define that inside utils function, and then we have to add inside utils there is corresponding header also, right, where I have defined that get32, not here utils.h. There I will define. Okay, so let's define that mem0 function, global mem0, and then mem0, what it should do, it has to, whatever starting and the length, it has to keep writing zeros. Okay, so that I'm storing that xzr inside that whatever x0 it is given, and I will try 8 bytes at a time, then subtract x1. So I go to the next address. Okay, after going to next address, I will basically set that to, if it is greater than 0, I'll set to, again jump to mem0, then again return. Okay, so this mem0 also I will put inside utils.h. Okay, so inside utils.h we have to basically define why it is not returning anything. Mem0, then unsigned long src, and then that value. Okay, that's it. Clean, then again build. Now what it is showing, utils.s, it is showing some issue. What is that issue? Okay, why this global is needed like this? Okay, so let's go to the boot.s code. Actually my plan was to basically use uboot to load this kernel image.img. so if I have to use uboot to directly load this image inside the RAM, so already that exception level would have changed, that GPU firmware would have changed the exception level from the EL3 to EL2. That's why if we try to access any EL3 level registers, it will create a synchronous abort. Okay, that's why in boot.s file we have to change some code. So wherever we are touching this EL3 registers, that I have kept inside if0, and similar setting we have to do for EL2. So basically hypervisor configuration register is also there in EL2. Earlier we are trying to jump directly from EL3 to EL1, but the GPU firmware has already changed from EL3 to EL2. So that's why now we have to do the settings in EL2 registers. So hypervisor, then status program status register, these two we have changed. Then ELR of EL2 I have updated with EL1 entry. So this code will be executed if one, right? So it will be loaded to ELR EL2 and then exception return. So it will jump to EL1. Okay, this is the only change with respect to the whatever we have written earlier in bootS.code. Okay, apart from that, I just want to add something in the main. So this we have already seen how we are sending it. I want to just add one thing, so that whatever characters that we send, we will try to print it here. Okay, so that's what I want to write it here. So I will be try to receive, if it is whatever is received here, whatever I will print there, then same thing I will send. So this is basically echo, whatever I will press in that serial console, same thing will be received here and same thing will be sent back, but that will happen after printing this hello world. Okay, so now let's test this build this kernel image, and let's test this image, whether we are able to basically see the UART prints or not. Okay, so let me just do some way. I think yeah, it was not visible, so I just made it visible. I will make the RPI. Okay, so it has built it, and now we can see kernel 8.img is there. So this kernel 8.img I will transfer from this Linux system to our Mac system through HCP. Okay, now I have transferred that same file is available in the this private /tftp.boot. Now let me open the terminal. Okay, so this terminal I have already tested it, but I will show you from starting. So in this one, let me first control control X. Okay, so I have used picocom to connect to that serial UART. Okay, so this is the command to connect through picocom, and baud rate is 1152. Okay, so that I have connected. Okay, so now the terminal is ready, and you can see here ls-l/private tftp boot kernel 8.img is present here. Okay, so just now I have transferred it. Okay, now I will power up that RPI. Okay, you are seeing that U-boot logs. Okay, then I will press enter to basically stop the auto boot, and I will do TFTP transfer of this kernel image at from here to here. From basically that will load this kernel 8.img to our RAM. I want to load at this location because this is what I have specified in linker script. Okay, one more thing I think I have already told, but let me tell you again. In linker file, right? In linker file we have basically placed all this starting of this kernel image we have pasted at this location. Okay, so this may be also one change which I did, and after that rest of the sections are same. Okay, that is one change. Okay, now let's bring that kernel 8.img in this at this location. So basically this kernel 8.img will be loaded at this location. Okay, so it has transferred. Now I will just read those locations just to see some those values are basically showing or not. Okay, those will be garbage, but just to make sure it has been written to that memory, I am reading that location. Now I will directly jump to that location 1 2 3 4. Okay, as you can see, hello world, whatever we have written there, it is coming here and it is waiting in while loop. Now if I write anything, it should come. So F I have written. So whenever whatever number I will press, that will go to the RPI, same character it will write back again here. Okay, so as you can see, right? So this basically this session completes here. Means we are able to bring up the UART on bare metal, and we are able to successfully run it on the RPI. Okay, so that's all I want to tell. And this code will be available in the GitHub. That will be public. That I will share the link also in the video. Okay, so that you can try it on your side also. Yeah, thank you so much.